Hello everyone, this is Dr. Feng Wang from my home. We didn't see each other for a while, although we don't have a regular classes as we did before. I hope we still have the same goals. Remember, the three goals: we want to learn some organic chemistry, we want to do some fun things. I want to help you guys to do some big and fun things with the friend around you. Well, one of the big things we can do with organic chemistry is to help people. Well, a big thing right now around us and around the world is the coronavirus. So, in the past few days, I read another paper about a coronavirus, a big, huge research team from Germany. They developed new ways to tackle the coronavirus. First thing they did was they determined the structure of the coronavirus, and they figured out the enzyme. This is the enzyme part of the coronavirus. That's very critical for coronavirus because enzymes actually chop off the big protein molecules and generate a small molecule, and basically the virus uses the small molecules to reproduce itself to generate more virus. So if we can find a good inhibitor that stop the reproducing process, we can kill the coronavirus. That's the basic things. I'm not a biochemist. That's what I read. As usual, I already posted that paper on Schoology. I know many of you will be biologists or biochemists or will be healthcare professionals. If you have any interest, you can read the article I posted on Schoology. So the inhibitor they developed actually is an organic molecule they call keto-alpha ketoamide inhibitor. So we see, oh, this is probably keto, this is keto, this is some amide, this is amide. There are many amide functional groups in these molecules. So this German team already tested this molecule in mice, and it worked. And hopefully they could move faster, and eventually we can use this inhibitor in human bodies to kill coronavirus before next winter. All right, so this is a paper just published in one of the top scientific journals called Science about 10 days ago, and I hope you will enjoy it. Now let's move to the real organic chemistry, the chapter 18. Chapter 18 is about aldehydes and ketones. Everything we are going to discuss in this chapter is about the reactions about aldehyde and ketones. Although we already learned many reactions of aldehyde and ketone in chapter 17 and some other previous chapters. So this is the structure of aldehyde, basically a carbonyl groups. One side is the alkyl group, and another side is hydrogen. Ketones, basically two alkyl groups attached to the carbonyl groups. So as usual, I would like you to read the naming part, the physical properties of aldehyde and ketones, because I don't think I can share much of the physical property with you. However, if you need some discussions with me on the physical properties, even namings, these molecules, you can talk to me anytime. So the key structural information of aldehyde ketone is this carbonyl groups. This carbonyl is the functional group because the oxygen is a very strong electronegative atom. It's going to pull the electrons away from carbon towards itself. Or we can draw a second resonance structure. So the resonance structure clearly shows this carbonyl carbon bears some positive charge while oxygen bears negative charge. So whenever we see charge is either positive or negative. Organic chemists are always happy because whenever we have a charge, we can do a reaction. So another important feature of this carbonyl groups is this carbon is sp2 hybridized. I hope by this time everybody know how to decide the hybridizations of carbons. That's what we learned in OChem 1. So this carbon has a planar structure, sp2 hybridized. The bond angle is about 120. So if we have a nucleophile, the nucleophile basically bears a negative charge. Nucleophile negative charge is going to attack this carbon. So if that's going to happen, the attack will be from both sides, the top side and the bottom side. Again, because the shape here around this carbonyl or around this carbon is a planar structure. So we learned a lot of preparations, reactions of aldehyde and ketones in the previous chapters. I'm not going to provide you details here, just a quick review like alcohols, primary alcohols that can be oxidized to aldehyde. Actually, this is one of the exam 3 questions. You have a primary alcohol, you have a secondary alcohol. The primary alcohol will be oxidized to aldehyde. So esters can be reduced to aldehyde. The same thing for acetic chloride, that can be reduced to aldehyde. This reaction is quite different. Basically, alkenes, this is called a hydroboration and oxidation reaction. It is a two-step reaction. The first step is the addition of this boron molecules to this alkynes. So you need to pay attention which boron or hydrogen will be added to this alkane molecules. The boron or hydrogen, which atom or group added until which carbon. So that will decide your final structure. The second step basically is oxidation reaction. The final product is aldehyde. Again, if you want to know the details, review the previous chapters. More preparation reactions for aldehyde and ketones. This is the secondary. Alcohols can be oxidized by many oxidative reagents to generate ketones. Acetic chloride react with the cuprate reagent to generate ketone molecules. Although Friedel-Crafts reactions, that's also a very popular reaction to make ketone molecules. Alkenes hydration under combined catalyst, sulfuric acid and mercury sulfonate. That's going to generate ketone molecules from chapter 11. All right, another reaction is oxidative cleavage of alkenes or ozone lysis. We normally call this is ozone lysis. Basically, ozone split the alkene molecules. So this is alkene. We have a carbon-carbon double bond. But this is also a two-step reaction. The key step is the first step. The ozone molecule will split these alkanes from the middle of the carbon-carbon double bond to generate a two ketone molecule. The next step, either with zinc water or methyl sulfide, to generate two ketone molecules. So the reactant is the alkene, basically is carbon-carbon double bond here. Ozone will split to two parts. Each part is either a ketone or aldehyde, depends on the structure of alkenes. This is also a reaction we learned in the redox chapter. Now, let's go to the real reactions of aldehyde or ketones. I already discussed the structural informations of this carbonyl groups here. Either this is a ketone molecule or aldehyde molecule. This is a planar structure. sp2 hybridized carbon. The carbon bears much positive charge. Oxygen bear a lot of negative charge. So it will react with a nucleophile because a nucleophile bear electrons that are not shared with anybody else. So they want to share the electrons with this carbon. So we can analyze the reactivity of this carbonyl compound. So very simple aldehyde, a slightly bigger aldehyde, and a ketone molecules. So ketone is the least reactive. So formaldehyde, basically the one carbon aldehyde, is the most reactive. The reason is first, you see the steric effect. You see this alkyl groups normally much bigger than hydrogen. So if you have a nucleophile here, the nucleophile will attack this carbon. So of course you have a bigger protections here. You have a less reactivity of, this carbon has a less reactivity because of the, you can call steric effect or the protection effect from the big groups here. So if you replace a big group by hydrogen, you increase the reactivity. Of course, you replace the two alkyl groups by two hydrogen atoms. That's the highest reactivity from the steric effect's point of view. The second reason for this reactivity trend is the electron. Basically, if you have more you have more positive charge here, you have a stronger reactivity. So from chapter, I believe chapter 16, we know this alkyl groups is a weak electron donating group, which means it won't push the electron toward this carbon. You see, this carbon bears positive charge. That's why it is reactive. Whenever you donate electrons toward this carbon, basically you reduce the positive charge in this carbon, so which also reduce the reactivity. So this is the least reactive carbonyl molecule in this, among these three molecules. Of course, two hydrogen, they do not donating, they do not withdraw. So this one is the most reactive among these three molecules. Again, organic chemistry basically is you just analyzed the structure, the charges of organic molecules. And so there is no way, at least there is no way for me to remember all the reactions. There are millions organic reactions. Basically, one structure is one reaction. So if you could analyze the structure, it's going to help you to remember all these organic reactions. So in my view, that's the core of organic chemistry. That's the core of education. Analyze the structure. Okay, first reaction is the nucleophilic addition reaction of a cyano group to a ketone or aldehyde molecules. So this is either a ketone or aldehyde molecules. This is a cyano group. Ca minus, this is cyanomer, very, very good or very, very strong nucleophile. Of course, this carbon bears a positive charge. So the strong nucleophile will attack this carbonyl carbon. So the final product is called a cyanohydrogen. So this is a cyano group. Hydrogen basically either water or hydroxyl groups, So the pi bond here, the carbon-oxygen pi bond breaks, and two new sigma bond formed. One sigma bond is between the carbon and a cyano group. The second sigma bond is between this oxygen and hydrogen. So one pi bond breaks, cyano groups added to this carbon. So two new sigma bond were formed during this reaction. So this is a generic reaction. This is an example. So this is the aldehyde. We know ketone can do the same reaction. Aldehyde react with the sodium cyanide plus the strong acid HCl and to generate a cyanohydrogen. Cyanohydrogen groups is the carbonyl carbon attached to the cyano group attached to the hydroxyl group. This is called a cyanohydrogen molecule. And let's take a closer look of this nucleophilic addition reaction again. This is a very strong nucleophile. Nucleophile bears negative charge, attacks the positively charged carbonyl carbon here. So we generate oxygen anion here. The next step is the protonation, because this is the acid we used, HCl. Acid condition, so of course we are going to pronate this oxygen anion to generate the hydroxyl groups. So the final product is the carbonyl carbon attached to the cyano group and a hydroxyl group. Again, this molecule is called a cyanohydrogen. This is a typical nucleophilic addition reaction. Positively charged carbon, negatively charged carbon, they react each other. So next reaction, I don't think we have this reaction. I'm not sure this reaction in this chapter or not. But cyano groups, if organic molecules attached to a cyano molecule, this type of molecule is called a nitrile, like alcohols. If you have an OH group, we call hydroxyl group, and these molecules are alcohols. For the cyano group, we call this group of organic molecules the nitriles. So nitrile is basically a big topic for organic chemistry, at least for the textbook we used. But I think it's a more advanced organic chemistry. So I don't want to cover a lot of reactions about a nitrile, but this reaction is a very common reduction reaction I want to share with you. So the cyano groups in nitrile can be reduced by lithium aluminum hydride. So this is a very, very strong reducing agent. Basically, we can consider this is like hydride. Hydrogen atom bears 2 electrons, so it is a hydride. It's an atom with a negative charge. So it is a very, very strong reducing agent. Basically, we just add reducing reaction. Basically, we add more carbon nitrogen bond. So you see the structure: carbon, no hydrogen here, carbon, 2 hydrogen. The nitrogen atom in the cyano groups also added was added to hydrogen atom. The final product basically it is primary amine molecules. It's a two-step reaction. I will not provide you details here, but the fundamental thing is the lithium hydroxide is very strong reducing agent. You can treat it as a hydride. So basically, you just keep on add a hydride to this cyano group. Eventually, you have the primary amine molecules. The next reaction we are going to discuss is called Wheating reactions. And before we discuss the details of the reaction, we need to know the reagent to do this Wheating reaction. A Wheating reagent, this is a Wheating reagent. Basically, it's phosphorus attached, three benzene groups plus the alkyl groups, but the alkyl group is a very special one. So this carbon here bears a negative charge, and this phosphorus atom bears a positive charge. So this called a Wheating reagent, or we have another name, is called a yellate. So yellate basically is a molecule with this type of structure of phosphorus atom with the 3 benzene ring plus a positive charge. The carbon alkyl chain, but the carbon here bears pure negative charge here. So this is called a yellate or Wheating reagent, and this is the reagent we needed to do the Wheating reaction. So actually, if I like the resonance structure, we can draw the resonance structure here. So the 2 electrons here, forms the covalence bond between carbon and phosphorus atom here. So in this structure, in this Lewis structure, each carbon here, the carbon here and the phosphorus atom here, they all have octet structure. But in this structure, the carbon still has octet structure with 8 electrons, but the phosphorus atom has 10 electrons. We know phosphorus, that's I believe it's a third rule element, so it can hold more than 8 electrons. And I like this resonance structure, and you know why. So this is a Wheating reaction. So if we have a Wheating reagent, this is one of the resonance structure. If I have Wheating reagent react with carbonyl, with the acetone molecules aldehyde. So the final product, basically the side. Let's take a look at the side of product first. The side of product, we don't care much. It's just the side product, or it's waste. This triphenyl phosphine oxide. The major product, the product what we want is alkene molecules. The alkene molecule is basically it's the aldehyde or ketone on one side, and the right side is basically the alkyl chain of Wheating reagent, the 9-phosphorus part. This is the alkenes, forms a new alkene molecules. Well, this is I have 2 examples here: aldehyde or ketones, either linear or cyclic structure. They react with the Wheating reagent or yellate to generate alkenes. Again, one side is the aldehyde or ketone. Another side is basically the alkyl chain of the yellate side. Here is the mechanism of the rating reactions, and again, aldehyde, this is a carbonyl carbon bears positive charge. It's going to react with the negative charged carbon. The oxygen or the pi bond is going to react with the positively charged phosphorus atom to form the rings, the four-member ring structure. A four-member ring, 4 is not a magic number, 4 is not stable. Then this four-member ring reorganized to alkene molecules. There are a lot of electrons movement. So when we do this type of movement, we form the final product, alkenes. So this is a very simple alkenes. When I say it is simple, because there is no E or Z conformations, either cis or trans. So if we have a cis or trans, or E or Z isomers for the weighting reactions, so it is possible to form E or Z. Both isomers are possible. Here is the synthesis of the weighting reagent. This is very critical. That's why we call this reaction it's weighting reactions. Aldehyde and ketones, they are very popular organic molecules. We can have a lot of weighting reactions. It really depends on how many weighting reagent we have. This is a process to make a yellate or weighting reagent. It's a two-step reaction. The first step is triphenol, 3 phenol groups attached to phosphorus react with alkyl halide to generate a phosphonium salt. Phosphonium, because this phosphorus atom bear a positive charge here, so it's called a phosphonium salt. So the halide here is just a counter ion to balance the positive charge. The next, this is very, very critical. We need a very, very strong base here. Because of the positive charge here, this hydrogen demonstrates some acidity. So if we have a super strong base, the base will deprotonate this protein to generate yellate. So protein goes to the base. The 2 electrons remains on this carbon atom. So this carbon atom bears a negative charge. So this is a yellate. Or we can draw a second structure. It's a resonance structure from here to here. So basically a carbon phosphorus bond here. I like this because, if you have a ketone or aldehyde, you have a yellate here. Basically, you just use this part as half of your final alkene molecules. Half of your alkene molecule. You use the ketone molecules, the residue of the ketone or aldehyde without oxygen, as the second half of the alkene molecules. Well, that's the weighting reagent and a weighting reaction. Here are examples to make some alkenes. This is a weighting reagent. You see, this is the second resonance structure. There is a double bond between this carbon and this phosphorus. This is aldehyde. We are going to have alkenes. The alkenes, the right side you see is the alkyl part of the weighting reagent. The left side basically is the aldehyde part without the oxygen. That's the alkenes molecules we are going to form from this reaction. So in this case, in this reaction, we have 2 options, either E isomer or Z isomer, although E is slightly higher than Z isomer because E is the trans, it's a more stable isomer than Z, the cis isomer. I hope at this moment you are very clear what is E, what is Z, which one is stable. So here I have quick test here for you to make this alkene molecules. And to save some time of this lecture, I would like you to spend more time, to review the reaction we learned so far and to decide how we make these molecules. And here, the next slide, I give you some clues before, whenever you make alkene molecules, use the yellate or weighting reagent. Basically, you need two parts. One part is the yield, another part is the aldehyde or ketone. So we can use either side as the yellate or weighting reagent. In this case, we use this side as the weighting reagent. Oh no, we use the left side. We use ketone for the left side. The right side is the yellate. So in the second synthetic rule, we use this side as the weighting reagent, and the right side as the carbonyl group to make the final alkene molecules. And why yellate a weighting reaction is so unique to organic chemistry? We have learned so many reactions to make alkene molecules. This is the one reaction we learned before. We have ketone molecules. We can do the Grignard reaction. This is the magnesium reagent or Grignard reagent. To do the nucleophilic addition reaction to make a tertiary alcohol. If we have a tertiary alcohol, we can do the elimination reaction to generate alkenes. But when we do this elimination reaction, basically we have two products. This is the minor product. This is the major product, alkenes. And I hope you know why this is a major product, this is a minor product. So we can make this molecule or we can make this molecule, but eventually we have a mixture. If the target is to make this alkene, we can make it, but the yield is very low, and it's probably hard to isolate this molecule from this molecule because the concentration is so low. However, if we use weighting reaction, we have a ketone molecules, we have a weighting reagent, we are going to have only one product. So the yield is pretty high, and we don't have to do a lot of isolation work because only one product generated from this reaction. That's, you see, when you compare the two reactions, both reactions can be used to make this molecule, but the advantage of the weighting reaction is pretty obvious. That's why the weighting reaction is basically a very unique. I don't want to say this is a very popular reaction we do every day, but it's a very unique reaction for organic chemistry. All right, time to take a break. Talk to you later.